Let's talk about how we can compare the side lengths and angle measures in a triangle. First, I'd like you to consider this question. How do you know whether or not it's possible for any three given segments to create a triangle? Will all segments make a triangle? Or will only certain ones make a triangle? For example, each set of three segments listed on the screen right now, do they all make a triangle? Is it possible? If not, why? Well, let's see. Okay, so our first set makes a triangle, and I notice that 7 plus 8 is bigger than 14. But my second set doesn't make a triangle. 7 plus 8 is equal to 15, and our last set doesn't make a triangle either. 7 plus 8 is less than 16. So what is it about these side lengths that caused some of them to be impossible to make a triangle, but one of them it was possible? What's the difference? Well, we actually have a theorem to describe this. It's called the triangle inequality theorem. And it states that in order for a triangle to be made from any three given side lengths, the sum of any two of them has to be bigger than the third. So if we go back to this example, you can clearly see that 7 plus 8, well, that's 15. And we have the segments 7 and 8 for all three of these examples, so it's kind of easy to compare. For our first example, 15 is bigger than 14, and therefore a triangle can be created from those side lengths. In fact, when you lay them all flat, you can see that the red one and the purple one laid flat is longer than the longest side, which was 14. So the sum of the two smallest sides was bigger than the biggest side, and therefore a triangle can be created. As opposed to our next example, where 7 and 8 are equal to 15, if you lay those two segments flat, you can see that they end up being the exact same length. So no matter how far you stretch 8 and 7, you'll never have enough left over in order to make a peak and therefore make a triangle. You really just end up with two congruent segments. And that problem only gets worse the longer that the third side gets. Like in this example, I see that 7 plus 8 is less than 16, so if I lay those two sides flat, there's no way for them to ever even reach the end of the third segment, let alone be long enough to make a peak. So our conclusion is that in order for a triangle to be created from any three given side lengths, the sum of the two smallest ones has to be bigger than the biggest one. We can expand this idea to describe relationships amongst the angles and the side lengths in a triangle. Knowing that one side is larger than another side, or longer than another side, allows you to conclude that the angle across from that side is larger or greater than the angle across from the shorter side. And vice versa, if you know one angle is larger than another, then you can assume that the side across from the larger angle must be bigger than the side that is across from the smaller angle. Let's look at an example. In this diagram, all three of the angle measurements have been provided, so it's pretty easy to identify that angle B is less than angle J is less than angle Q. But based on this information, we can also conclude which sides are shorter or longer than the others. Since angle B is the smallest, and JQ is the side that is across from that smallest angle, we can assume that JQ is the smallest side. Angle J, being 53 degrees, is the medium angle measurement, so you can assume that the side across from the medium angle is also the medium length side. And lastly, since angle Q is the largest angle, you can assume that the side opposite from it is the longest side. So we can write this all as one inequality, showing that JQ is the smallest, and then QB is second smallest, and JB is the longest, and that's all in relationship to which angle was small, which angle was the medium, or which angle was large. We can come to similar conclusions if we're given the side lengths instead of the angle measures. On this diagram, it's clear to see that CT is the shortest, WT is the medium length side, and CW is the longest. Therefore, we can assume that angle W is the smallest angle because it's across from the shortest side, and that angle T is the largest angle because it's across from the longest side. And that would mean that angle C is the medium angle because it's across from the medium length side. So we can write this inequality. Angle W is less than angle C is less than angle T. And that's because W was across from the shortest side, C was across from the medium length side, and T was across from the longest side. We can combine everything that we've learned so far to express what values of x would make a valid triangle for triangle PHV. Now, you might be saying, wait, we don't have enough information. I only have 2 of the 3 angle measurements. But since it's a triangle, we know that it has to add up to 180 degrees, and therefore we could calculate that the missing angle measurement is 68 degrees, which means angle P is the smallest, followed by angle V, and angle H is the largest. And that would mean that side HV is the shortest, and side PH is the second shortest. But remember what we said earlier in this lesson about the relationship between the 3 sides of a triangle. In order for a triangle to exist, the sum of the 2 shortest sides has to be larger than the largest side. So I could write this inequality to represent that relationship. HV is the shortest side, PH is the second shortest side, whereas PV is the longest. In order for this triangle to actually exist, the sum of the 2 smaller sides must be greater than the third side. So I can substitute in each of the algebraic expressions I see for the side lengths of this triangle, combine like terms, and solve the inequality. And we end up with an answer of x is greater than 4, which means any value for x greater than 4, you could plug it in and find a valid triangle, or vice versa, any value of x that's less than 4 would not make a valid triangle. Let me show you what I mean by picking a number. Well, let's pick a number that's bigger than 4, like 5. So if I plug in 5, I would have 7 times 5 plus 1, which is 36, and 4 times 5 minus 4, which is 16. The sum of 36 and 16 is 52. Let's compare that to plugging 5 into this side length. 9 times 5 plus 5 is 50. So yeah, the sum of the 2 shortest sides, being 52, is longer than the longest side of 50. So a valid triangle could be made using those side measurements. But let me show you the other direction as well. Let's imagine a number that's less than 4 instead of greater than 4, such as 3. If I plug in 3, let's see if we get another valid triangle. I'll do 7 times 3 plus 1, well, that's 22. And 4 times 3 minus 4 is 8. So the sum of 22 and 8 is 30. Let's compare that to 9 times 3 plus 5. That would be 27 plus 5, which is 32. 32 is longer than 30. So that shows that if I were to plug in a number that's less than 4, the side lengths here would not be long enough to even reach the end of this longest side, let alone make an actual peak to make a triangle. And that's all you need to know about inequalities in one triangle. In the next part of this lesson, we'll be discussing inequalities in 2 triangles. In other words, how can you use some given side lengths and angle measures to conclude whether other side lengths or angle measures are greater than or less than the given ones.